Again, those of you online, if I talk too fast, please feel free to tell me to go slower. So again, today, so last time, Mary talked about sort of some of the chemistry of making and mixing the chemicals to make aerogels. And she left off with the production of a wet gel. And so the next step is to dry the aerogel. And that's what I'm going to talk about. And I'll review a little bit again about aerogels. This is a nice way of classifying aerogels that I found in the reference down here. So you can talk about them in terms of their appearance, and I would call that their form, which could be a film. You can make a thin film of aerogel. They also can be made in powder or a granular form, and I know that some students here have worked with the granular form of aerogel, or they can be in monolith form. And a monolith is one piece. And the picture that many of the pictures Mary showed yesterday were one solid piece. And much of the work that we do is with monoliths. And then you can talk about aerogels in terms of their composition. They can be organic, inorganic, or a combination of the two. And yesterday, Mary talked about the silica, the inorganic. And tomorrow, you're going to talk about some of the organic.
More inorganic and organic.
Yeah, so she'll talk about those others more. And again, most of our work is done with the inorganic materials, as is much work in the aerogel world. And then you can talk about their microstructure, and that has to do with the pore size, the distribution of pores that you get there. They can be microporous, mesoporous, or mixed size. And a lot of that has to do with how they're prepared. Again, to remind you of some of the properties of silica aerogels, the content, really kind of the density, I guess, is what they're talking about here. In terms of grams per centimeter cube, it can be as low as 0.003 to 0.2. Mary talked about zero gels. Those are not properly dried and they tend to be very dense. So they'd be much even higher than this, maybe 0.5 grams per centimeter cube. They're very porous. So again, Mary talked about when you make them, they're full of air. I don't think we've ever made one that was 99.9%. Typically 95 is sort of where we are with them. The diameter of the pores, the mean value is sort of 10 to 30, but there is a distribution of pores. And I'll talk about that next week. The size of the diameter of the actual solid material is on the nanometer scale. And again, that depends on the conditions that you make them with. Specific area or surface area is very high, and that is one of the very attractive things about aerogels. Young's modulus has to do with their strength, and that's typically megapascal. It has to do with how they deform, for those of you who aren't engineers. Shear modulus has to do with their strength also. That's hard to quantify, and it really depends on a lot of things, so there's a big range here. So again, this is just a review of what Mary talked about making the silica gel via the sol gel process. And she talked about starting with the silica alkoxides. Right? She talked about the SiOR. That was the TMOS or the TOS that she talked about. And then she talked about those reactions, hydrolysis and condensation. And she took you through some of those chemical structures, which I'm not going to do. But just again, this is sort of the procedure. You mix the TMOS with the water, and you have this hydrolysis reaction. And then you have these condensation reactions where you're either producing alcohol or the water, and you form this wet sol gel, right? And again, the purplish is meant to be the silica clusters, and the gray is the solvent that's in there. And I think she left off sort of at this part. So I call it the hard part. All of it's, a lot of it's hard, but this is really is how do you dry the wet gel? Okay, that's the key to making an aerogel, right? You can make your wet gel with your solid material surrounded by the solvent. And if you just let it dry, you make a zero gel. And you can see the structure has shrunken down a little bit, a lot actually. And you can make a single solid piece of zero gel if you dry it very slowly. And if you dry it too fast, you get pieces of dense sort of material. But if you can remove the solvent without causing what's called this pore collapse, you can get an aerogel. So see, the aerogel structure is the same. We've completely replaced the solvent with air, and I have the same structure. It hasn't collapsed. And that's the challenge, and I'm going to tell you a little bit about why that is a challenge. And then I'm going to tell you how that challenge is addressed. Okay. So what's hard is that wet gel is this nanoporous structure, really small pores, surrounded by this liquid, you know, the solvent, whatever it is. In the case of the silica aerogels, we make its combination of methanol and water, or ethanol and water, depending on how you make them. And there's not a whole lot of solid material there, right? Because these things are, again, like 95% air. And so when you dry the silica gel, the wet gel, you have evaporation at the surface of the gel where the solid materials are. It has to dry out. And then you get capillary flow, and then you have to get the stuff out of the structure. And so what happens is capillary forces, surface tension forces, they're the same thing, people call them, these are words we use, becomes really important. It's a large value. And that's the problem with drying. It's just, you can't just remove the solvent. It's not easy. So if we look at those capillary stresses, this surface tension pressure here is related to gamma, which is the surface tension of the liquid vapor interface. So it's a property that depends on the two things that are there, the vapor and the liquid. So depending on those is a property of a system. And so if you look at, imagine this is a pore wall of diameter D. So, you know, it's like a cylindrical, in this case, we're modeling it as a cylinder. So I have my solid phase here. Okay, I'm talking about silica. That's the silica, okay, where that's formed. And then it's filled with this solvent. And in the case here, we don't have complete wetting, and you get a meniscus. Okay, you form the meniscus. And that meniscus has some radius of curvature on it that is related to the angle between the liquid and the solid surface. Okay, so for the case of it being greater than 0, this radius, Rm, is just the diameter divided by 2 cosine theta. If your surface is already wetted, right? So we've got the solvent all along the surface, and maybe that surface has a thickness delta. And then Rm is just by pore diameter divided by 2 minus delta for theta equals 0. Okay, so again, theta is the contact angle of the liquid on the solid. G is the diameter of the pore. And delta is the thickness of the liquid layer absorbed on the solid surface for complete wetting. So I'm doing this, I'm going to show you some numbers so that maybe you'll believe me that it's a hard problem from this. But so it's related again to that surface tension and the size of those pores. Okay, and when those pores size is really small, Rm is really small and P is really big. That's the problem that we face when we're trying to do this drawing. Okay, so the thickness, that delta, it depends on a lot of things. Temperature, vapor pressure, hydrogen bonding between the liquid and the solid, many things. But you can have a maximum pressure is given here by this equation, and that's when you're at this case. And so you can calculate some different values of that force, and in here, in this case, it's in terms of pressure, but for different diameters and for different sorts of solvents. And so, for example, if you have pores in your structure that are 5 nanometers, which is on the size of what the aerogel structure has, or the wet gel structure has, filled with water, your capillary tension can reach 1,000 bar. So a bar is an atmosphere. So 1,000 atmospheres. So 1,000 times this, which is very, very high, right? So that's the challenge, is how to, so when that force pulls on the structure, it breaks it. And so we have to be able to reduce that. Now you can see if we use different solvents there, and I'll get to it later, but one of the techniques for drying the aerogels is to replace whatever's in there with something that's less, it's going to cause less force. So here it's much less. So if there's hexane in those pores and you have to get rid of the hexane, the force is going to be much less, so the pressure. Is that clear? Does anybody from the internet have any questions? I was afraid to open this because I never know how to close it. Okay. Again, if you have questions, I don't really see like hands up, so just yell at me. I'm good with that. Okay, Mary, how do I get back?
You just minimize that one.
Just minimize? Oh, this is great. Thank you. We use Zoom, not Teams, but this is good. I'm learning a new one. Okay. Okay, so again, here's that cartoon of the wet gel with the solvent. And here's sort of a zoom in on a pore wall, right? So this is the solid out here, and this is the pore. Okay, and here is the pore. It's been dried, and this is where that solvent still exists. And those forces are pulling on that surface, and they will collapse if you don't do it right. Okay, so that's the challenge of drying. And so all I tried to show with that, I think you believe me now, that's the hard part. And so what I'm going to address as we go forward is different ways of doing that. But I want to talk about what are some of the things along the way that matter. And so this is a way you can sort of talk about the process before drying. You have these chemical reactions. This is where we're mixing the TOS or the TMOS and the methanol and the water and the catalyst. And you form a sol, and then it gels. One of the steps in making an aerogel is aging, which is important because, and I'll talk about why, it allows the structure to get stronger. And then you can do surface modification. So the starting chemicals, again, Mary talked about this yesterday, can be an alk oxide type, or it can be, a lot of people use something called water glass. We do not. Mary, you're talking a little bit about water glass tomorrow. It's another silicon starting point. Your solvent, again, remember she talked about adding the alcohol in the water. It can be composed of several compounds, and so sometimes people will use what's called a drying control chemical additive, DCCA, or some sort of surfactant. Do you know what a surfactant is? It's a chemical to reduce surface tension. So when premature babies are born and they can't breathe, they give them a surfactant. So that's how I think. Well, the first time I've heard of it. You may have a different word, but we call it surfactant. So what? Yes, that sounds like to lower the surface tension. So same thing. If you can lower the surface tension on the structure of the aerogel, you can dry it better. And then Mary talked about you add water to allow that hydrolysis to take place. And then she talked about catalyzing that reaction using either an acid or a base catalyst to do that. And so as an example, why I say one of the things that affect drying behavior has to do with those steps. What are you mixing in the chemistry? And this is a schematic. This is an excellent reference on drying of silica aerogels. Just the structure you get depending on whether you're an acid catalyzed gel or a base catalyzed gel can be different. So that's going to affect the drying behavior. Am I slow enough? Okay. My students, when I go back to New York, I'm going to tell them that I spoke very slowly. They will not believe me because I go very, very, very fast in English. Okay. Okay, so another thing, we just talked about that. I mentioned aging. We haven't mentioned aging before, right? So we have whatever the chemicals we react, make that sol and you get the gel, and then aging means waiting. Aging means growing old, but in this sense, well, they are growing old, but not years old. It's faster than that. But what happens when you age something is that even after it's gelled, those chemical reactions keep occurring. And so you can still get changes in the structure. So you get new cross-linking. And so maybe where you had these two bits of silica, we showed that pearly chain, they're connected, but as they age, you get new linkages, and it increases the modulus, is like the strength of the gel. Okay, so it's just it's there, and it instead of being connected like this, it gets more connected. And so that's one of the things that aging does. And this sort of shows these sort of silica groups. And as it ages, the shape is shown with the dashed lines, kind of structures. And so aging can be accelerated, by temperature, by pH, water concentration. There's lots of things that you can do to change aging. And so this is, again, another important step in the process of making an aerogel. And then the last thing to talk about before actually getting to drying methods is to talk about surface modification. And so this has to do with sort of using these surfactants. So as the wet gel dries, the pores start to flatten. Okay, so here's my pore, and it starts to flatten, and then the particles get closer together. So by flatten, I mean the pores are like this, and maybe they get more like this. And then the particles are closer. Okay, and then they continue to condense like they did during gelation. And so when you're done, I may have started out with a structure that is open like this, but now it's collapsed a little bit. So it was like this, and now it's kind of gotten smaller. And again, these are all sort of silica, and this is, these are on the scale of nanometers, and this area here is sort of that open area that we want to keep open. Okay, but if we're not careful, as it dries, it becomes denser. So you make a denser a heavier aerogel than you would want to. So you can do surface modification. So it's chemical treatment of the solid phase can be performed before you try to dry it. Mary talked about this yesterday when she talked about using a co-precursor. She talked about at the end of her talk the hydrophobic aerogels. So you can, again, with silica, we use TMOS. You can use something called MTMS or some of the other examples she gave. And she talked about how that worked, and that makes the surface more hydrophobic. And so you can do that when you mix chemicals, or people also do that. They take the wet gel and they soak it in something else, like hexane or something like that, before trying to dry it. And so what happens when you treat that, so this is now, we have a treated surface here, right? Instead of just the OHs, we have this treated surface. You dry it, it might shrink, but then it doesn't condense and form new bonds and springs back. So here it is originally, here I'm drying it. At the end of drying, it's gone back to its original shape. And that's achieved by using surface modification. These are surfactants. You're trying to do something to lower the surface tension on those. Okay, so those are some things that affect the aerogel, the drying. So now we can talk about drying. And so the big challenge is to get the liquid out of the pores without crossing a phase line. And so I've got a phase diagram here. Many of you may be very familiar. Many of you may have seen this in chemistry and not looked at it again. But this is a plot of pressure versus temperature. And it exists, all substances have phase. So that depending on the pressure and temperature, the substance could be a solid, it could be a liquid, or it could be a vapor, or it could be a supercritical fluid. And so things like triple point, you probably the same word in Italian. I don't know, triple point, right? Is where a substance exists as a solid, liquid, and vapor, or all three phases can exist. And then the critical point, above which you have the supercritical fluid. And so my example is water, although there's a fallacy in my drawing here because water expands on freezing, so this line goes the other way, but ignore that. So in the solid form, right, if I'm at 1 atmosphere in less than 1 degree C, it's ice, right? So it's in the solid form. If I'm at 1 atmosphere between 0 and 100 degrees C, I'm a liquid. And vapor form, if I'm at 1 atmosphere greater than 100 degrees C, I'm a vapor, right? That's simply what a phase diagram is. And so now we can talk about drying. And here's that phase diagram again. So I'm looking at a phase diagram of the solvent that's in the wet gel pores, whatever that is, right? And the ones that Mary talked about, and I'm going to talk about TMOS because those are the ones we always make. What's in there is methanol, water, and probably some unreacted TMOS, right? So something in there, but it's in liquid form. And I need to get that liquid out of there. And without crossing this, so this line is the line between the liquid phase and the vapor phase. And I don't want to cross that line because that's when I'm drying it and it collapses. Now, I do have something there that crosses the line. It's a special technique. I'll show you that. So the three methods that you can do that are used is one is freeze drying. I cool my substance, right? And then I evacuate it like a vacuum, lower the pressure. So I make it colder, lower the pressure, then I can go directly from a solid to a vapor, sublimation. It's called sublimation. I can do that. That's one way to avoid I'm trying to avoid crossing this. That said, you can cross the line using, it's called ambient pressure drying. So you stay at, again, that same, this is sort of ambient pressure. I don't have to raise the pressure. I just have to heat it, right? I dry it by heating the material. And that can be done with the use of these surfactants and other chemicals. Okay, so if I treat the surface, it might shrink and then it will bounce back. Okay. The other way to do this, and the way that aerogels were discovered through this supercritical extraction process, and then the other techniques people have tried to put in. The other way is to bring my liquid, don't cross this line, bring the liquid up to a supercritical point. So this is my critical point. Again, it's a function of whatever the material is. And when I get to talking about that method, I'll show you what they are for different solvents. If I bring it up here, so that the thing about a supercritical fluid is there is no phase boundary. And I will show you that. I have a video that shows you. There's no phase boundary. There's no partial liquid, partial vapor. It's just a supercritical fluid. If you can do that and then lower the pressure, you avoid crossing that line. You can make an aerogel. So there are advantages and disadvantages to each of these methods depending on what kind of aerogel you want to make. And so what I'm going to do is take you through, I think I'm going to go, we'll take a break just after 11 because we started late. So we'll go to 11 and take a break and then we'll start. So I'll start with the first one, which is ambient pressure drying. So ambient pressure drying just means that it's, again, you're not pressurizing it. You can do this in an oven. You don't need special, well, you need venting equipment, but you don't need high pressure equipment or anything like that. So the idea, I start here, right? Remember, this is pressure versus temperature. Stay at the same pressure and just kind of heat it up. And the way I do that is with these surfactants. So here's that picture schematic of a pour. Solid, there's the pour, there's the solvent that's receding, you're trying to get out of there. We've got our surface tension, but if we coat the walls with a surfactant, we can do that. It'll lower the surface temperature. You know, under certain conditions, you can lower the surface temperature. In theory, it sounds nice. In practice, and I'll show you an example of what people do. We do not use this technique to make aerosols, but it requires a lengthy solvent exchange to do that. And so this is just an example from the literature of somebody who made silica aerogels via ambient pressure drying. And they do what's called a two-step modification. Remember I talked about you could do the surfactant by adding something in the beginning to your chemical recipe and or soaking your wet gel in something. They do both. And so here's an example. They start out making the chemical recipe. They use tetraethyl orthosilicate, TEOS, the precursor that Mary talked about, plus ethanol, plus methyl trimethoxysilane. When I first met Mary, I could not pronounce any of these. I have learned how to say these because I use them in the lab, but MTMS is how we refer to it. Mix that. And then they mix it with water. Remember, she talked about you mix the chemicals, you got some water, and they use an acid catalyst here. And then they stir this, they form the sol. So that has started the hydrolysis reaction. And then they stir this for like 8 hours. Remember, Mary talked about TIOS has longer chain and it takes longer to get this to happen. So 8 hours. Then they add their base catalyst. And then they form their gel. So here's their silica sol. Right, they got the sol in there in 8 hours. And then they get alkogel, wet gel, alkogel. Mary's used both. Sol gel, which is not technically correct. Do it for 8 hours. Then they age. Remember, I talked about the aging step, and they do that in a closed container for 5 hours. So they just wait and let those reactions continue so it strengthens. Then they do surface modification. That's that surfactant thing. And remember, I talked about you could soak the wet gel in something. And so they soak their wet gel in a chemical, I don't know, TMCS, ethanol, and N-hexane. So these chemicals are designed to reduce the surface tension. So they do that for 2 hours, 2 hours, I'm sorry, 2 days. So for 2 days, they soak the gel. And what they're trying to do is they want to remove the whatever's in there, ethanol and water, whatever's in there, and they want to replace it with these chemicals that will lower the surface tension of the material. And then they dry it. And what that just means, they just heat it, okay, at pressure. And they eat that, and they do it slowly. You can't do it fast. So they do 9 hours to do that process. Okay, and they are able to produce silica aerogels that way. So that is that I added this is their from the paper. I added the things in red to indicate the time, because this is one of the problems with this method. But this is, 3 days or so to do this process, which is a long time. What happens when you make ambient pressure dried aerogels? It's a very good process for making these granular aerogels. Again, this is a product I know that Professor Buratti uses here in a lot of projects. They are made by ambient pressure drying. Cabot Corporation makes them. I don't think Aspen makes them. No, Aspen doesn't. I don't think they make them. And this is what, and this is one of the more commercially available products is these granular aerogels, because in many ways they're a little bit easier to make. I wanted to find an example of Cabot Corporation's process. They don't share. It's their secret how they make it, but it is known they do ambient drying, and that's how they're able to make large volumes of it. And these granules are very good for many, many things, because you can insulate very well with them, and they're relatively inexpensive compared to like the monoliths. The other thing you can do, because of that surface modification with these, is you get these really interesting springy. So this was an aerogel made in a test tube, and you can bend it, and it goes back, and it doesn't break. But you can see its color is opaque. And we point this out because we're in the business of making transparent aerogel. So this won't work. I say it won't work for that. There has been more recent work. There is a company in Japan that makes monolithic translucent aerogels. They won't share how they do it, but we have a colleague who went and worked with them and said weeks weeks. Takes a long time to do it this way. So some of, yes,
The bendability of the aerogel made with the surfactants, a characteristic that the aerogel have only with the production system with the surfactants. So if you make it with the supercritical drying, your
they are
aerogel-
not, yeah, I don't know, let's see. You could probably, I'm just looking at her, this is the, I think if you did it with, well, we did do it with Stephen Gayson. You could do that with supercritical.
If you did it with the co-precursor,
Yeah, you have to, yeah, yes.
so as opposed to adjusting it afterwards, if the co-precursor were in there so
Yes.
that the network is less connected together, then there can be some flexibility.
Okay.
Yeah.
Okay,
Yeah, so-
it doesn't depend on the drying system. You can
No.
with the drying
Right.
system you want.
But it depends on the chemical
On the
connectivity.
chemical.
Right, so for the audience, the question was, can you get the bendable aerogels with wrap with a supercritical extraction? And the answer is, if you use co-precursor to do that, you can get some of that, but in the supercritical extraction, well, the CO2, they might treat the gel before. So it depends on the method, so there's two ways, the co-precursor or the exchanging with the other thing.
Yeah.
So-
The critical was just an example.
Yes.
Was just for saying that
Yes.
it's a characteristic
Yes.
only from
It's an interesting characteristic. We had a project with a student who was working with computer scientists making soft robots. So imagine a robot that could squish down, go under the door, and rescue people or something like that. So that was the idea, and so we started saying, gee, could we do that with aerogels? We tried, we didn't get very far, but it was an interesting idea. Could you make an aerogel? So he put, we call it muscle wire. If you have a wire and you apply a voltage drop, it contracts. You can make the wire contract. Unfortunately, it broke out of the aerogel, but anyways, it was an interesting project that is short-term project. We didn't try for very long. I still think it would be useful to, but these are really interesting aerogels. This is from a group in India, Dr. Rao, who's been in the aerogel world forever. He came to visit us and he showed us these aerogels. It was very cool. Very cool. Okay, so ambient pressure drying is a suitable alternative or a suitable way to make aerogels. It's cheaper because it doesn't require, it's considered cheaper because it doesn't require expensive equipment. But it does involve surface modification and strengthening of the network. It takes longer, and you use these other chemicals to do this, which are not necessarily good either. So they do show good properties, though, depending on what you're looking at. They do have good porosity, low density, low thermal conductivity, compared to what was originally done with supercritically dried aerogels. But again, the processing time is very long. It can take days to weeks. That example I showed you was 3 days. If somebody's there doing everything, it takes it longer. And large amount of chemicals, again, some of which are hazardous. Probably many of which are hazardous. Okay. Should we take a break now? It's 11. Let's take a break. Okay, we'll take a break and we will do, I was told last time, it was too short, 15 minutes, okay?
Okay.
15 minutes, and I think I'll be able to finish the rest of that. Okay, 15-minute break. We'll start at 11:15.
Okay, thank you.
Yes, bye. do this right. Okay,
Yes, I had another question.
yes,
And I almost get the fact of why we should not cross the line between liquid and vapor, but I'm not very sure. Because I think that we don't need to cross that line, because to cross that line, we have to increase the temperature, and for the capillarity, the vapor will create something like 1,000 bar, and then the aerosol will
yes,
explode, let's say.
Yes.
Is this the reason why we
Yes.
we can cross?
yes, because when you're on that line, you're in the vapor dome, we call, where you have a mixture.
Yeah.
Some liquid, some vapor, some gas, what you want to call it. And then you have this phase line, and that causes what you just said.
Okay,
It causes it to
okay.
collapse.
So again, if you go back to your diagram with the, there.
Oh.
So the top of the diagram on on the little one, right.
Sit.
On the left, you can see that the pore has collapsed on top.
Right.
Where the gas
Yes,
is.
yes.
And it will continue to collapse if the
As this
liquid
dries.
starts to evaporate. And so by coating the surface, adjusting the surface, and reducing the surface tension, there isn't as much force and therefore not as much force.
Right, and that force is right here. That's where, as that's drying, proceeding, it's
Different, it collapses in different places.
Right.
Okay, so it's nothing. I was thinking that it's something about exploding. So you have to push so much with temperature to.
yeah. So
Well,
it's a
now the
force.
vapor,
It's pulling it together, not
Oh,
pushing it
pulling it
apart.
together.
Yes,
Okay.
yes. Good question. Okay, where was it? I think this was where we left off. Okay, so now I'm going to talk about freeze drying, which is another method to go around to avoid crossing this line. Yes, no, good.
Another question, sir. I want to clarify another thing. So the 1,000 bar pump, what was about? Was the fact that I was saying, so the pressure you need to use to pull out the liquid from the aerogel, or it's the fact that when you, as you said, when you dry and the water comes out of the pore for the effect of capillarity, or like.
Yeah, it's related, it's the pressure on this pulling them together. It's not the pressure that you need to pull it out.
Okay.
Yeah, it's not, no, we call it a pressure, it's really, think of it as a force. It's the magnitude, related to the magnitude of force acting on those surfaces, and it just pulls them together. Because they're not strong enough to combat
Keep it-
that.
to keep open.
Yes.
Okay.
Okay. So this other method involves freezing and lowering the pressure, and then sublimating. So it's called, when we freeze dry a wet gel, people often call that a cryogel, for cryogenic temperatures, although I don't think they go quite that cold. So the example is dry ice. You know dry ice? So when you have dry ice, when you go to a bar and they want to look cool, at ambient temperature and pressure, it's down here. It's going to sublimate, so it looks like this. You go from solid directly to gas, and that's kind of the idea. So again, you freeze the gel, you lower the pressure, and then you allow sublimation to happen. And so here's an example of, from another reference from the literature, of somebody doing this. This is a silica aerogel. They started with, their precursor system was the MTMS, in this water glass is another precursor that marries. I don't know, I'll be honest, I don't know to what degree the MTMS is important, but maybe it is. But what they do is they, again, do 2 days of gelling and aging. So they let it, they mix it, it gels, and then they let it strengthen a little bit by aging. And again, the red is me to emphasize the time. And then they freeze it. And they go to minus 83 degrees C in this case. And they get sort of, they call it an ice cube, frozen. And that takes about 8 hours. And then they lower, so they freeze it and they put it under a vacuum, right? So they lower the pressure and then they heat it from minus 83 to 23, right? And this is what they're doing. Freezing it, lowering the pressure and heating it. This is the process they do. And they end up with sort of this in this particular case, they end up with this sort of granular looking aerogel. And again, this is like a 5-day process to do this. And generally results in, it does result in opaque materials. I've never seen a transparent freeze-dried material. This is initial work. This is a product called Aero Clay. And this was used to oil spill cleanup. So this is oil and it's picking up the oil. So that's an application for aerosols because it has a lot of surface area can pick up the oil. But you can see these are broken powders. Now, more recently, and I don't know how they're doing this because they don't tell, which is a company, they have produced a product that looks like this. This is, I believe, they do it's like a clay thing, silica and clay. There's people have produced silica, cellulose, clay, graphite, and carbon aerogels by freeze drying. This is an example from the literature. That's this one. They actually tell you how they made it, and that was similar to what was done above. So it is cheaper than supercritical drying, the thought is, but it's not widely employed because you get crystallization of the solvents. When you freeze it, it crystallizes. And I look closely at this, and I think I can see some of that in these materials. But I think they're promoting these as good insulators, and I'm sure that they are. So that's sort of new that people do that. Okay, so the method that was used originally, the aerogels were invented in the 1930s because somebody supercritically dried this wet gel and found an aerogel. So again, the pressure, temperature, and the idea is to raise the temperature and pressure enough to stay in the liquid form up to supercritical state, and then you lower the pressure to get around that liquid vapor line. And this is a video, see if it works. So this is a video made by a colleague of ours at Union College. This is carbon dioxide. So this is the phase line. So it's in a glass container that is sealed on the top and bottom. You can see these bolts, and then they're going to heat it. Okay, and so you watch the phase. So right now I have 2 phases, the vapor or the gas and the liquid. And as you heat it and you reach a supercritical state, there's no phase line. Okay, it's what's called a supercritical fluid. That is the idea of this. And now they're cooling it. And now I have the phase line comes back. Okay, I have 2 phases, a vapor or gas, and it's vapor / gas, we call it the same thing, and a liquid. Okay, so that's sort of the idea. Because if you don't have the phase line and you just have the supercritical fluid, you don't have that surface tension problem. Okay, so that is, again, this is how aerogels were first invented or discovered, and this was in the 1930s. Okay, and again, you avoid that liquid vapor boundary line by bringing the solvent above its supercritical point. There's no liquid vapor interface and no capillary stresses. due to the meniscus. Because remember, those forces are where you have the liquid and the vapor present. So there are 3 types of supercritical drying. We call them high temperature, and I'm going to go through each one of them, where you directly heat up, you make the wet gel with the alcohol as the solvent, you just heat it up and extract. There is the low temperature method, which was, I think, the 70s they invented this. Instead of the high temperature, they soak you exchange the alcohol in the wet gel with carbon dioxide, which has a lower supercritical temperature, and you do the extraction. So I will call these alcohol supercritical extraction, ASCE, so that's high temperature. Low temperature is carbon dioxide supercritical extraction, CSCE. And then the third method is called rapid supercritical techniques. And that is the method that we use. We developed it based on some work at a place called Lawrence Livermore National Labs in the United States. They had developed a method, and we read about it and modified it a bit. And here's a lovely picture of an aerogel. That one's huge. That is nice. Okay. So again, going back to that pressure temperature diagram, this is that critical point. When we get to these pressures and temperatures, we have that supercritical fluid. And so just as a reference, water has a critical temperature of 374 degrees C and 221 atmospheres. That's very high. Okay. Methanol has a supercritical temperature of 240 degrees C. Methanol and ethanol, which are what are in the gels we make, about 240 degrees C, much lower supercritical pressures. And then as you go down all the way here, you can see carbon dioxide. The supercritical temperature is only 31 degrees C, much lower, so you don't have to heat it as high. But it's still got a pretty high pressure, so it needs to be able to withstand the pressure, but it's lower temperature. Okay, so the technique used for these high temperature alcohol supercritical extraction is typically you have some sort of, this is a pressure vessel, right? So this is thick wall, metal, bolted down. And you might make your gels. This particular example is from Dr. Rao in India. You make your gels perhaps in a test tube. So those are here. And you take the whole volume inside, all of the inside of this area. You fill it with alcohol, the same alcohol that is in the gels. And so that would make, if it's TMOS, it would be methanol. TOS might be ethanol. And then you heat the whole system. Sometimes they pre-pressurize with a nitrogen gas. They can do that. This is from their drawing. They use a pressure gauge. So they watch that. They heat it, and because it's confined, the temperature, as you heat it, the temperature and the pressure will go up. And you can bring it up to that high temperature. And again, if we're talking about methanol, you want to be above 240 degrees C and 81 bar. So your pressure vessel has to be able to withstand all of that. And then they have, you have some kind of valve. They use vapors too. Some kind of valve to, when you get to that pressure, you open the valve and you let the supercritical fluid escape. Then you cool it all down and you have an aerogel. So this is much faster than the other methods I showed you because you're not doing any solvent exchange. You're making the aerogel, sticking it in, so they might make the aerogel, maybe they age it a little bit, I don't know, maybe in a few hours. They put it in here in maybe 4 or 5 hours, probably a day in this method to make an aerogel. But There's significant safety issues with this because you have this entire volume filled with a flammable liquid, right? There's a classic case of a factory burning down, blowing, exploding because of this method. They still use it in some places. Some people still use it. So yeah, it was in the 80s that this was developed. The low temperature CSCE, CO2 supercritical extraction, was developed in 1985, and this is widely used. This is probably the most popular method, supercritical extraction method used to make aerosols. And so again, this is actually the pressure temperature phase diagram of CO2, and here they have solid liquid gas, which I'd be okay with that because CO2. But the critical point is just much lower, high pressure, but much lower temperature. And so what you do with this method is the same thing, you make the wet gels. And the issue with this method that can add time is you make the gel in some container like a test tube. And then you have to get it out of the container, especially if you want a monolith, one piece. So to do that, you have to let them shrink. So if you leave it gelled, and maybe you seal it, but maybe you open it a little bit and you let it shrink a little bit, then you can take it out. Often they'll break the tube and try to get it out, something like that. And then typically, again, talking about TMOS, you've got a water, methanol mixture in there. Also, I should point out, in some of these direct methods like this, you really have some water and some methanol. So you have to go above the 240. You don't have to go this high. That's very high. You have to go a little bit above. So the next step is they typically exchange a solvent in the pores for a hexane or an acetone first, because that's better with the CO2, correct, Mary, the chemist?
Yes, because the CO2 is not polar, and so it's hard to directly exchange with CO2 and the water alcohol mixtures. You won't be able to get all of them out of the pores and then end up with pore collapse. So you have to put something in which the CO2 is more miscible.
Yeah, so
in there first.
Right.
There's a lot of solvent exchanges.
So you do this step, and then you exchange the new solvent. So then you take your wet gel, which has shrunk a little bit, that you've soaked in hexane or acetone maybe for 24 hours or something like that. And then you put it in a critical point dryer or an autoclave. It's a pressure vessel. And you exchange with liquid CO2. And I think I have this picture of, this is some work that people have done. So you take so here now is, and this one is sideways. Was here? Sideways, actually. So here is the inside of my pressure vessel. So this is a metal, thick-walled, can take very large pressures inside. And you put your sample, what do you call it, wet gel capsule. So they put their sample in there after they've soaked it in hexane or acetone or something. You put the sample in, and then you fill this up with carbon dioxide. Okay, so you put that in, and then you heat it. And again, as you heat it, the pressure goes up. You have to, sometimes they pre-pressure it with nitrogen, but you have to be careful. You have to be able to heat it. And you only need to heat to a little bit above 31 degrees, 35 degrees. And as you do that, because this is all confined, the pressure goes up. And then they release the pressure. So once you get to the point you want to be, you open the valve. You got to be careful. This is, I'm sure some people have automated this, but a lot of this is, you have to watch it. You have to release the valve slowly. If you open the valve fast, you have nothing. Okay, so you can do it. And this is also a longer process. And again, this one can take days to weeks to do. But the advantage of this process is that you can get these big, beautiful, monolithic aerogels using this process. So it's similar length, say ambient or freeze drying. but you're capable of making really big monoliths. So this is a, I think this was like, that's like 24 by 24, okay, 20 centimeters, 40 centimeters by 40, big window that they made in, I think this one was made in Sweden, but you can see these are big, huge pieces of aerogel. This is not as big an aerogel, but these you can buy from a company online. You can make the big things. You cannot, again, freeze drying, ambient drying, not ones that you can look through. Again, ambient drying, I showed you the ones, but they're all opaque. This method is used by, there's a company in the United States called Aspen Aerogel. They're another big commercial producer of aerogel material. And they make, Cabot Corporation also makes blankets. And what they do is they use, they have very large pressure vessels. They have a blanket, like a woven fibers that they dip in the sol gel, the precursor material. And they roll this thing up and they put it in a big autoclave and they process it. So this has, we blanket with aerogel in it and it's very insulating. And this is a big commercial product that's used to insulate pipes and things like that. And they use this method. But you can see you could not get this, you know, and I showed you the picture on the first page. You can't get that with those other methods. So supercritical extraction is the thing that is used for that. Okay, which brings us to the rapid methods. So RSCE is rapid high temperature technique. And this one was developed at Lawrence Livermore National Labs. It's in California in 1996. And this operates at high temperature. It's a high temperature method. We call it relatively safe because it doesn't have an excess amount of solvent. So the problem with this method is this whole vessel is filled with the alcohol. And the rapid methods, so this is, I'll take you through their particular method. They have a mold. So it's a mold, metal with a hole in it, and they pour the aerogel precursors in. So they're going to make an aerogel that looks like this size. This is probably cylindrical. And this is metal, and the whole thing is in a vacuum chamber. And what they do is they heat the entire, they don't add any, they don't solvent exchange. They don't add any additional alcohol. They just heat the wet gel. And it's in this confined mold. And as they heat it, and it's a little hard to see, this is temperature versus time. And this one, let's see, this is their, okay, temperature here, pressure over here in English units of pounds per square inch. That's like an atmosphere would be down here. So what they've got here is I think this is the right time. Yeah, okay, temperatures and safe. So they heat it. What's going on here is their heating pattern, the temperature versus time. And as they heat it, suddenly, you know, the thing is full. It's not completely full because you can never completely fill it, but the solvent expands, the whole thing, and then the pressure starts to rise very fast. And so you're able to achieve the kind of pressure you need, which supercritical in pounds per square inch units, it needs to be about 1,500 PSI. Anyways, and then what happens is once it reaches supercritical, they have a pressure relief valve here that says, oh, we're at 1,500 PSI or supercritical pressure, open up, and slowly open up. And that's this. And then they release it, and then they cool it down. And this is very fast processing. So they have made, we have made small ones in 60 minutes. Using this method, they can process these materials in 60 minutes, which much faster than 7 days or 3 days or whatever. So that's one of the advantages to these methods. Some people don't like them because they're still high temperature. Okay. But the advantage is not excess, like there's no more alcohol than what's in the gel. So it's less dangerous, I guess, than the other techniques. And it doesn't involve solvent exchange. So you don't have all the excess solvents that you have to recapture and do something with. So, yes.
I'm not an engineer, so sorry for the question, but you pump the vacuum on the not on the mold but outside to avoid dispersion. Heat dispersion.
This, I think they have so they do that, I think, to insulate the material.
Yeah.
So it's in, with their method, I also think this is they have a box here also as a safety precaution. So it's like in a pressure vessel.
You never know.
Yes, it's a mold in a pressure vessel, right? Their mold is probably bolted together. Actually, I think I have a picture of it. But sort of a safety thing too, that's inside of the box.
So it's more for safety than for insulation, in your opinion?
I think it's probably both. Okay, definitely more for safety than I think they don't have to evacuate it, but I think that gives them the insulation so they don't have to heat it as much.
Because the pressure reached are very, very high.
They are very high. Yes, yes. Okay, so here's a picture of that's their mold that they use. And it's interesting because studies of this process, they were working on it until 2002. And they did some interesting work. This is showing, this is where they made the aerogel inside this pressure vessel. And they did some studies looking at, so if you have this vessel, and again, you have a wet gel that you're heating up, you have a supercritical fluid, you have to get it out of there. And the only way it can get out is to go here, out through the top. And so they were looking at, well, how do the properties of the materials change if you're at the top of the mold versus the bottom? And so they did some work on that. This is a plot of the longitudinal sound velocity versus the radial position at different locations. And from that, they were able to get some density interest in that. And so they did some work optimizing that, but then their funding, their last papers talk about funding ran out and they didn't continue it anymore. But then in 2002, I had a mechanical engineering student who saw a picture of an aerogel and said, I want to make an aerogel. And I think I said this on the first day, but came to me and we went to Mary, and we did not have the pressure vessels that people use, the autoclave for the CSCE, the carbon dioxide supercritical extraction. And so I said, we went to Mary and we talked to a few other people, and we had a colleague who had a machine like this. And this is a hydraulic hot press. All it does is it has two platens here and here, and you can close it and you have a force. The hot press applies a force and can seal something in there. So here's my platens, right? This and this. If I put a mold inside there, I can have a force that holds it together. These are used to make laminates, composite laminates. A lot of times you can heat it and you can press it. And so I had a colleague who had one of these, and we came up with the idea to use this as our pressure vessel. So the way we make an aerogel is we have a mold, again, just metal with a cavity in many different shapes. And we will put our chemicals inside here. And we put some sort of gasket material to seal it, because you can't just have metal on metal. We use graphite. And then we use the platens to seal it. So now it's a sealed thing that we can heat and make an aerogel. And I can show you the steps that we use, called rapid high temperature technique, rapid supercritical extraction. So this is the press force. This is the time, and this is the temperature. And in the first step, we fill a mold with the aerogel chemicals. and we close the mold and we seal it. So that's the step. Okay, so the press force, we ramp it up and seal it. So, okay, and during that process, and then we start to heat it. Okay, so the next step is to heat it, and that's shown here with the temperature line. So now we start heating it. The mold is heated. During heating, we say we pour liquid in, not gel. In fact, that's a factor when we make them. If they gel, we can't pour the liquid in. So gelation, and I'll show you some videos of what we learned about gelation if I have time. Gelation occurs, and then we keep heating, and we say that's when it strengthens and ages. Now, this is 1 hour. Most people do 4 hours. But remember, I told you that things like temperature can affect aging. So we are getting sufficient aging because we're able to make aerogel. So we get some aging in there. And so then, once that's happened, and at this point in time, and I'll show you a temperature pressure trace, we're supercritical. And so then we extract. This is the extraction. So the press force drops, right? I started out with 250 kilonewtons holding it together, and I slowly reduce that. And when I reduce the force, the gases escape. Okay. So that's our supercritical extraction step. Instead of using a valve, we use this. And then what's sitting in the mold is a hot aerogel, and then we cool down. So those are the 4 steps. And we typically do this in 6 hours. We take a process that's about 6 hours. We can do it faster for smaller things, but when we want to make large monoliths, we do it about 6 hours. And it's a nice technique for making aerogel. So here's what's happening. This is a phase diagram again, pressure versus temperature. And this is that vapor line for methanol. Right over here, I'm a liquid. Over here, I'm a vapor or gas. And this is it for water. Again, we have a mixture. So the mixture has some line between that. So what happens in our process is as we heat a little bit of heating, and then once the whole mold is filled, you get a rapid temperature rise. So the temperature goes up. Sorry, rapid pressure rise. So the temperature rise is creating the pressure rise, just like the other techniques. What happens in our process is then we reach a point where we're at supercritical pressure, but not at supercritical temperature. So we're still over here. We have we call it the leak point. The force from the liquid inside pushing on the hot press balances the hot press force. They're equal. So to equilibrate, a little bit of that methanol escapes. And not quite supercritical, a very little bit escapes, which is a safety thing for us. We don't want it to get the pressure to get too high in there. And then when we get over here, so this is kind of, we call it the leak point. This is the extraction. This is where I'm releasing the hot press. I'm lowering the hot press force. And I have the hot aerogel, and we cool it down. So the advantages of this method are it allows for rapid fabrication of monolithic aerogels. Right, 6 hours. Very easy. You literally mix the chemicals, put them in, press a button, leave. 6 hours, you come back, you have it. If everything works out, aerogel. It's also nice because it's reduced chemical waste. We don't have any solvent exchanges. We do release this methanol, and we're actually talking about how to recapture some of that, but it's a very small amount. It's only what's left over in the wet gel. We say it's inherently safe because of the hot press, the way it works. Even if it fails, it maintains the force. It will never just let go. And it's applicable to a lot of different types of aerogels, and Mary's going to talk about some of that tomorrow. Disadvantages include it is still high pressure. It is still high temperature. And a hot press, the hydraulic, it costs $50,000, more than a critical point dryer. Although a big critical point dryer probably costs that much too. Yeah. So, you know, those things. And it is, again, it is a high temperature. So there is some danger there. But again, it's a smaller amount of stuff. So where are we? Okay, let me just show you some. This is kind of a fun project we did on our process. So we wanted to, when we first developed this, we wanted to figure out what was going on when we didn't know what, we just knew we got an aerogel when we, I mean, we knew the process. We wanted to see what was happening. So we had a student actually who was from the Czech Republic. He came over and worked with us for, Union College has an exchange program, and he was there for the summer. This was a summer project. I think, yeah, because his master's he did something else. So we made an optical mold. So a big piece of metal with a hole in it, and there's glass. So here it is in the hot press. There's a little chamber where we could put the aerogel precursors in. We have a camera and a light source. And so we could watch what was happening as we did our supercritical extraction. And during this, we took it through the process like we normally do. And we had some sensors to record temperature and pressure. We took some pictures. And so this is an image. So we're looking at the aerogels. Right now they're a liquid, and we're going to heat it. And so we can see some motion in there. So we discovered we have the two things. We have convection, we have motion. We didn't know that before we did this. And then we also found that we have darkening. So as we watch this go on, you can see it's getting darker and darker. So we looked at the video images and kind of estimated convection velocities from around 1 millimeter per second is what we're seeing. And we distinctly would notice it would stop moving, which we said, that's when it's gelling. Like it was a way for us to tell when it was gelling. And then we also noticed this darkening, which becomes even more obvious as you go along. And we had seen darkening before in other studies, but we didn't have independent recognition of stuff. So let me go to the next one. Oops. So what we did is we took images. So here's, and this is just lighted differently, but you know, here's an image at initial time, later time, keep going. It looks like that. And we could see that it was dark. We have to be careful because things are happening around the outside. So we would image a little bit of this in the inside. And here you can see this is initial time, later time, longer time. It's getting darker. And so what we were able to do is plot things like the intensity versus the temperature and the intensity versus the time for different heating rates. Like we heated it really fast or slow. And these little pink things are the observations of there no more motion in it. And we were able to sort of understand a little better when it was gelling and what was happening in the thing. And from that, we found that we could integrate, if you look at temperature versus time, we could integrate and come up with a correlation. But what I want to do, because I'm about to run out of time, is just show you this one last thing. We also use this. So we were trying to make a different type of aerogel from titanium, a titania aerogel. And we could never make them monolithic. We could make something. We didn't know what was going on. So we did this, use the same thing to make a titania aerogel. So we're just again looking in the mold. And this one you can't see as much motion. Maybe you can't see as much motion on this one. But we're going to start to see it darken. So it's going through that whole process of heating, darkens. Now we do, so let's say, I think it starts to leak at some point. That's the aerogel. And then watch what happens. And really shrinks. Poof. Gone. So we were able to, by doing this a number of times, plotting again that pressure versus temperature relationship. So here's that image at A, just kind of heating. And then up here, we think it's gelled, starts leaking. We've clearly formed something here, D, formed an aerogel, which was really interesting because it really shrunk, because our silica aerogels don't shrink. And then this is E, when we released the pressure, it's gone. So it didn't have the strength to, number one, withstand kind of the extraction bit from that. We went on and we stopped making titanium. We made titanium silica aerosols like that, and that worked out well. Somehow we got the strength of them. So I'm just about out of time, and I am not going to talk about this stuff. I do just want to get to the very end, which is, so again, using this process, we can make these really nice. So this is an example. This is 14 centimeters by 14 centimeters. We can make up to 13 millimeters thick. This one is only 5 millimeters. Mary showed this yesterday. We started out making them this size, just smaller. This is maybe, it's a half inch. It's like 10 millimeters. On the, yeah, yes. And that's what we started making them this size, because we were doing things with them, testing them. And then we got involved in sort of making these windows. So we've scaled up to this size, which is still not big enough. But it's a function of our hot press, the force that it can do. It's only in English units, but it's 60,000 pounds of force, whatever that is. And right, so the other feature of ours is they don't shrink. No shrink. That titania shrunk, but our silica does not shrink. And we have good thermal conductivity, good density, and good surface area. And then I'll be talking about sort of some of the aesthetics of these aerogels. We do use laser etching to make patterns on them. It's really cool. It's on the word. I'm talking about that in a few weeks. And then just a little on the industrial. What do they do with it? Industrial production of silica aerogels. I mentioned most of these as we went through this. Silica and carbon-based dominate the production. We don't do anything with carbon-based, but there's some people that are making insulation products. And again, the major, I took out air glass, really doesn't exist anymore. Really, the major ones, at least in the US, are the Cabot and Aspen. I know there's some over here. Well, Cabot is also over here. American Aerogel Corporation, I think they're still in business. They make carbon-based. Yeah, but Aspen and Cabot in the US are very established. They are expensive for that. Oh, and here you go. Here's something besides these. One of the big things is, where do you get the silica from? The precursor to make the aerogels. So there's a lot of work going on with these, rice husks, all kinds of bio production. We don't do anything. And Mary, you're going to talk a little bit about that tomorrow, right? Yeah. Okay, I think that was all I have. All right, it's just a summary. Oh, and we will share the link. There's a movie about making aerogels in our lab, but we won't show it today. Maybe I'll show it one time when I finish earlier. Okay, that is all. Any questions from anybody? Sorry to the online audience, I didn't stop and ask you if you had questions before. Nope. Okay, well, we will tomorrow. Mary will be talking about some more on the chemistry and the different types of aerogels that I think will be of interest. Okay. Yes.
Thank you. I would like to say you that if you want in the next days, tomorrow or next class, if you want to show to the students that are in class some samples of aerogels in order so that they can touch, they can see. Yeah. I have some samples, so you can take and to show them the samples, okay?
Okay, great.
So if you remember to me, tomorrow I can give you to Mary or you, to of you the samples so that they can see and touch, okay?
Thank you.
That would be an advantage of coming to class.
Yes, come to class so you can touch them. Okay, thank you.
Okay.
All right, bye-bye.
Bye, thank you very much.